two solid bodies rotate about stationary mutually perpendicular intersecting axes with constant angular velocities omega 1 and omega 2. Find the angular velocities and angular acceleration of one body relative to the other. So let's consider this is a rigid body, and let this is rotating about, say, x-axis with an angular velocity omega 1. Clear? So this is x-axis and this is y-axis, and let this is z-axis. So we have another body, and this is suppose rotating about y-axis with an angular velocity omega 2. Clear? So these two are rotating with constant angular velocities omega 1 and omega 2, and these are two perpendicular axes. This is along y, this is along x. Now what we have to calculate? We have to calculate the angular velocities and angular acceleration of one relative to the other. So we have to find, suppose, angular velocity, relative angular velocity of one with respect to 2. So for that we need omega 1 minus omega 2. Clear? Here omega 1 and omega 2 are mutually perpendicular to each other, so we can have this omega 1 2 is equal to omega 1 square plus omega 2 square. Clear? So from here we can write 3 square plus 4 square, and we get 5 radians per second. So up to here the question is relatively easy. Clear? But in order to find this angular acceleration, relative angular acceleration, it is somewhat difficult. So for this I am going to use three different approaches for solving this problem. And the first approach is, suppose I want to calculate the angular acceleration of one with respect to 2. As this problem is associated with rotating frames, here one frame is rotating with a given angular velocity. So in the first approach I am using a basic definition approach, in which suppose we have a vector v, suppose vector v, and this is a vector that is rotating. This vector v is rotating in frame, say fixed frame, and that frame is, say, f1. And we have another frame, I name this as f2. This frame is rotating with angular velocity omega 2. Clear? Then we have a formula about the rotating frame situation, for which we can write dv, where v is the vector that is associated with frame 1, that is a fixed frame. So that dv by dt, and that is associated with frame 1, and that is equal to dv by dt associated with respect to frame 2 plus the angular velocity of the rotating frame and its cross product with the vector associated with frame 1. Now here we are taking this vector of frame 1 as the angular velocity vector. So from here we can write d omega 1 by dt in frame f1, that is equal to d omega 2 by dt, sorry, this is d omega 1 with respect to frame f2 plus omega 2 cross omega 1. Now the angular velocity is constant as the axes are fixed and the magnitude is fixed. So this part is 0 in this fixed frame. So we have 0 is equal to the angular acceleration of 1 with respect to 2 plus omega 2 cross omega 1, or from here we can write alpha 12 is equal to omega 1 into omega 2, as omega 1 and omega 2 are mutually perpendicular to each other, so we can have this result. Clear? Now omega 1 is 3 and omega 2 is 4, so from here we can write 12 radians per second square. So this is the first approach for solving such kind of problems for relative angular acceleration. Now the another approach, and for moving to another approach, look at this figure again, that this omega 1 I am taking along x-axis, this omega 2 I am taking along y-axis. Clear? So in another approach, let we have a point P, and that is on the first body, and when the body rotates, this point will move in a circle. Clear? So this is the axis, x-axis, and it is rotating, the body is rotating with angular velocity omega 1, and when this body rotates, let this angle described is say d theta. Now suppose a person is, or an observer is here, so initially it is at point P and then it is at point P dash, and it is observing the rotation of the another body or any other point on the another rigid body. Clear? And this is rotating about y-axis with angular speed omega 2. Now say this observer is observing any point of the another body. Clear? Let this point is Q. Now with respect to this object 1, we can write this as omega 2 and this as omega 2 dash. Clear? Omega 2 and omega 2 dash, and this angle is d theta. Now this arrow represents the change in the angular velocity. Clear? Now from here we can write this d theta is equal to dw2 by magnitude of these arrows here. Omega 2 is equal to omega 2 dash, so we can write this as omega 2. Clear? So if I divide this result both sides by dt, so I will get d theta by dt is equal to 1 by omega 2 d omega 2 by dt. Now this d theta by dt is for this object 1, so I can write omega 1 and this is omega 2, and this is the angular acceleration of 2 with respect to 1. Clear? So angular acceleration of one object with respect to another can be written like this also. Clear? So this is our method second. Now I'm moving to the third method to solve this problem. So for this, concentrate on this result, the relative angular velocity of 1 with respect to 2. So in third method I can write omega 1 2 is equal to omega 1 minus omega 2. Now I can write omega 1 I cap minus omega 2 j cap. Now if I differentiate this equation, d by dt omega 1 2 it is equal to d by dt omega 1 I cap minus d by dt omega 2 j cap. Now from here I can write alpha 1 2, that is the relative angular acceleration of 1 with respect to 2, and here omega 1 di by dt minus d by dt omega 2, and here we have dj cap by dt. As the angular velocity of the first object with respect to which we are calculating the angular acceleration of 2, so this part is 0. Clear? And here we have to be careful that here we are trying to calculate this dj cap by dt. Now this dj cap is not a unit vector. Clear? So this dj cap is something else. Now how we will calculate this dj cap by dt is our concern here. For this you have to consider the situation of object 1. Let this is any point that is moving in the circle with respect to point 1. Clear? And this point, the point through which the x-axis is passing, now this x-axis is towards u. Clear? And we have two mutually perpendicular axes. This is y-axis and this is, say, z-axis. Clear? Now this object 1 is rotating with an angular velocity omega 1. Now as this object rotates, so consider this rotation of y-axis. Clear? Now suppose this variation in the orientation of this axis is, say, d theta, and this d theta is very small, and j cap is in this direction, so this is also the direction of j cap. Now this arrow is representing the change in dj. Clear? Suppose the magnitude of this variation is ds. Clear? And the magnitude of this unit vector is j cap. So from here I can write d theta as the ratio of ds by the magnitude of this unit vector, and this is 1. Clear? Now here this dj cap is parallel to z-axis. Here you can see that this dj cap is parallel to k cap, or you can say that this dj by dt is also parallel to k cap. Clear? Because if I write in this form, it will not change the direction of this dj. So here dj cap is parallel to z-axis, so this is z-axis. Clear? And this dj is along this z-axis. Now this dj is a vector, and we know that a vector has a magnitude, and the magnitude is the length of this vector, so this magnitude is ds, and it has direction, and the direction is along z-axis. Here we have shown the direction of dj, that is along z-axis. So this part is the magnitude part, and this is the direction part. Clear? So from here we can write dj cap by dt is equal to ds by dt k cap. Clear? And ds by dt, from here you can write that this ds by dt is basically d theta by dt k cap, and this d theta by dt is for this object 1, so I can write this as omega 1 k cap, and this is dj by dt. Now you can substitute this value of dj by dt here in this result. So we will get alpha 1 2 vector is equal to minus omega 2 omega 1 k cap, and taking the modulus on both sides we can write alpha 1 2, and that is equal to omega 1 omega 2, and we get the same result.